All right, everybody. I wanted to go ahead and summarize the lecture that we did on day 2, the day before the exam, just to kind of get a clear picture of what we covered, etc. So, first, we wanted to get an idea of what happens, rather, what's essential for us to do is get a clear picture of the motion of objects when the velocity is changing, either speeding up or slowing down. So we reviewed constant velocity motion, and we concluded a couple of things. First, if this is graph A and this is graph B, what we concluded is that A is faster than B, is faster than B, and we know that object A is faster than B because the slope of the graph is steeper. This is at constant velocity. Okay. The other thing that we realized is that in a graph like this represents moving backwards because the slope is negative. We'd actually plotted that in the Buggy Lab. So continuing with this idea, what we basically did is we used these two features of constant velocity and modified them to better understand what's happening when the velocity changes. So to this end, we noted that if I have a graph like this, the whole time that I'm looking at a graph like this, the slope is always positive, which implies that we're going forward. The other thing, though, is that we're flat here and steep here, so that means it's speeding up. And all three of these graphs represent the motion of an object that's going forward and speeding up. Now, with the velocity graph, it was a little easier because our slope starts off at 0, so that's 0 velocity, and then positive slope means positive velocity, so we're able to connect the lines here. But then we came up with the third rule that said when you're looking at an acceleration graph, the sign of your v graph slope tells you your acceleration. Regardless of what you think it's doing or what I think it's doing, it tells you what the acceleration is. Regardless of what you or I think it's doing, we just use the sign to guide us. So here's a positive slope, positive acceleration. Negative slope, negative acceleration. Negative slope, negative acceleration. Positive slope, positive acceleration. And just to back up a little bit, so that's how those two graphs relate. In other words, we get the acceleration graph by looking at the velocity graph, not the position graph. Of course, next, the idea we want to take a look at is what these various position graphs mean. It's written here, and so the ideal for your final exams is that you actually get these memorized so that you can describe them to somebody who's asking, describing a problem. Meaning you should be able to look at a graph and tell me what the object is doing. And we have two things that we need to describe. Is it going forwards or backwards? Is it speeding up or slowing down? So just really quickly, this is going forward and slowing down. This is going backwards and speeding up. And this is going backwards and slowing down. Now, in the interest of time, I'm going to actually let you figure out why that is. And in order to do that, you're going to really need to carefully look at the arguments using these constant velocity graphs, not to answer, but rather to guide you to your answer. After that, we did a little practice with vectors. And I'll insert just a little kind of side thing here. So we talked about vectors. And basically, as far as we're concerned, a vector is an arrow with a length and a direction. and we think of it as kind of being a little part. It's like we're taking it's like a shorthand for a triangle with an arrow at the end, where this is sort of the hypotenuse. This leg has a length of v sine theta. This leg has a length v cos theta. And we actually labeled them according to the sides of the triangle. So this is Vy, this is Vx. And this is a tool that we used when we studied projectile motion on day 3. But I wanted to make sure that we kind of had that labeled now. Then Mr. O'Connor came and talked a little bit about Circaf stuff. That's an outside issue. Important for IB students, but there's really nothing to summarize there from my end. Then we did that little bit of practice with vectors. We broke for lunch after practicing for vectors, and then we did our marble drop lab. So if you recall, we had a lab where you had a little buggy, and you had a marble. And the idea was that the marble dropped, and the buggy had to roll up and catch it. And what we realized is that the marble equations could be expressed vertically as y is 1/2 gt squared plus v naught y plus y naught. V in the y direction squared is v naught in the y direction squared plus 2gy. And vy equals gt plus vy naught. Before you panic, you gotta ask yourself a question. What does the y mean? Why all these subscripts? Here's the idea. We're basically saying the vertical direction is y, and the horizontal direction is going to be x, just like in the coordinate plane that you're used to in math class. Now, the equation for the buggy was simply x is v naught xt plus x naught. And we were able to actually figure out how far back the buggy needed to be to catch the marble. Most people got around 20 centimeters. Anywhere between 10 and 20 was the order of that distance. And we got some really good video. Now here, I'm going to actually do a quick little solution. We did this problem. Based on the buggy lab, what we realized is it's obvious that the marble gets one equation and the buggy gets another. And we took the same logic to solve a problem where you have a ball launched horizontally. And we want to know where it will land. If we call this x naught and this x, we want to know how far from the edge of the table it is. So we set up an equation in the x direction, and we said basically x is v naught x times t plus x naught. And so we said x is 2 times t, and we said, okay, we can't figure out how far it lands from the edge, only from the x equation, so then we had to actually look at what happens to it vertically. And what we concluded is v naught in the y direction is 0. V naught y is an unknown. We don't know how long it'll take to fall. We know the acceleration is equal to gravity. And we know that we'll call its initial y position 0. And the position it lands at when it falls is the height of the table, which is 1.5 meters. So now we can go ahead and plug in to the formula. Y is 1/2 gt squared plus v naught t plus y naught. And let's remember, g is the acceleration due to gravity, so we're going to make this 10 meters per second squared. So when we plug in, we're going to get y equals 1/2 times 10 times the unknown t squared, and this y is 1.5. So we end up getting t is the square root of 3/10 when we isolate. I'm going to leave you to do that math. So you need to do this algebra. Okay? So t is the square root of 3/10. And when we actually solve there, what we'll end up getting for our time bear with me. is about 0.55 seconds. So now we have the time to fall, and just like with the Marvel Lab, we used the time to fall to figure out how far back the buggy needed to be. We're going to be able to use time to fall, and that's exactly the same horizontal distance that the ball spends off the edge of the table landing. So we'll take x as 2 times 0.55, and we end up getting 1.1 meters. So that's the idea for, that's kind of basically what we did for the second day of class. It's a good summary of what we covered. One thing I'll say is I'm definitely thinking about giving a quiz on Monday, so you may want to review this problem. We'll do a bit of work with this problem again in class before we do anything. Actually, you know what? I won't give you a quiz. I'll put this on your practice exam because you'd expect a horizontal launching problem on your test on Tuesday.